Hello and welcome to another lecture. In this lecture, we're going to go ahead and design a concrete slab on grade. Now, we're going to use the code in the United States, which is ACI 360R 10. Let me show you the code for a second. Here's the code right here, and has about multiple chapters, and they got a bunch of good examples in the end too. So this is the code we're going to follow. Let's go back to the PowerPoint. Before we do the design, I'd like to kind of do just like a preview a little bit and what we're talking about. So look at these. I was walking in Home Depot and Sam's Club, and I saw these, and I said, you know what? Let's work on the design of concrete slab. Look at these massive racks and all the weight on top of them. Some of them are just like the weight is on top of these posts coming down, and the aisle is basically just a foot or nothing in there. And that creates a negative moment. Like if we draw a picture of it, you're going to see have the positive moment underneath and negative on the top, which you got to watch out for cracking right here. So we got to guard against that. And when you look at this, there's two different type of design. Two different type of method we can look at it. Of course, multiple method we're going to look, but I'm just going to talk about the loading itself. One is the wheel of the it could be a loader, or it could be a forklift like this one here. And then the other one is the post load right there. So we kind of show them right here. There's some good reading here. You can take a look at this and you can go over it in class. If Chapter 7 I like best on ACI 360. I mean, for a thickness design method. So one of the biggest things you want to design a slab on grade, you got to be careful is how the module subgrade reaction. You need to have a geotechnical engineer give you that, the K factor. How much is it? And a lot of time in my experience, I've seen a lot of, sometimes the slabs fail, not because of the slabs, not because of the design, just because the subgrade failed. So the subgrade is really, really important. So you get that done first. And in fact, let me show you this. And a lot of designers, sometimes they put this in their design. They say, due to lack of specific geotechnical information, this slab has been designed using a subgrade module of this and that, and therefore the designer is not responsible for it. So subgrade is very, very important. So make sure you get that done. Don't just go ahead and pick up a table and get a number from it. So one of the things we're going to look at is how thick the slab should be, what strength concrete should be using, 4,500, 5,000 pound. Is reinforcement required? Where is the joint should be placed, and how to control crack and stuff like that. And when we look at the slab, you got to look at what is causing the failure and how can we guard against it, and that's how we design it. And here's 4 different type of failure. One is the failure of the slab when the slab develops tension stress. And then the other one is a bearing failure and punching failure and bearing stress on the dowel itself. So you as a designer really got to check all these stuff. Minimum required slab thickness based on allowable bending stress, and then do the shrinkage and temperature, and do the estimate crack width, and we're going to design it based on the fluxual stress first, and then do the bearing stress and punching shear and bearing stress. Here it says this strength of the concrete is nearly significant to slab design, so there is no need to check the shear strength because the other stuff are more powerful, can control it. The only thing you want to worry about is a punching shear. I do have a video on a punching shear for a footing, so you can watch that if you want. Again, one of the biggest important things is chapter 5. Let me go over the ACI code right here. Take a look at chapter 5, and has the loading right here as an introduction. And it says there's a few different type of load: a vehicle load, concentrator load, distributor load, line and strap load, which is a pound per foot, and usual load, construction load. A lot of time, construction load might control in a regular building that the slab is basically made for a foot traffic. But during construction, you're going to have equipment, scissor lift, loader might even be on top of the slab, or pickup truck, or they put all their material, they load them on a slab for the building. So this might control, but anyway, then you have environmental load. Let's go back to the PowerPoint. And construction load, just kind of talked about, kind of important. Yeah, there it is. Construction load, pickup truck load, scissor lift, concrete truck, dump truck. Concrete truck is pretty heavy. Dump truck, hoisting equipment, tilt wall erection, and setting equipment. All this stuff makes it heavy, and you kind of guard against that. And table 5.1, which we'll look at it will give us the capacity of the either forklift or the loader, and the weight of the vehicle plus the capacity, and then what is the wheel spacing. Because you need this in the design. There are multiple design methods. One of the design we're going to use is the Portland Concrete Institution design method. And another thing which kind of I like is the factor of safety are you're going to add to the slabs. And based on the load type, if it's a moving wheel load, you can go up to 2. I will preferably use 2. And you really can not go wrong if you use a factor of safety as 2, because we're using allowable stress design here. And one thing I do not like about the code should really allow, and I will get into this when we do the example. You can see that I used to operate a loader, I had a picture of him someplace, I'll show it to you later. A loader, and then sometimes when you have a heavy load, you end up on both wheel, and then the operator might panic and drop everything, so you end up with the impact load. Unfortunately, the code do not allow for that, so when I design it, I'm going to add impact load. We'll talk about that in a minute. But anyway, this section is about the module of rupture. Module of rupture is important, and a lot of time when we design a slab on grade, we're going to use module of rupture of 9 times square F prime C. And you might see a table has a different type of a MR, like 7, 6, 8, but 9 is a common one. In reality, when we taught reinforced concrete design, the module of rupture, we used this equation here. So minimum requirement for slab, I like chapter 7. Let's go to chapter 7 of the code. And they're using a thickness design method. This is really good. There are 4 different cases. Case 1, wheel load close to the corner of the slab edge, and is given by these equations right here. You have to put in factor safety, and then there is your FAT tension, and there is L, which we talked about in pavement design. L is the radius of relative stiffness, and we do an example. We will go over these things. Then case 2, wheel load considerable distance from the edge, and you have case 3 and 4, and this is one method you might want to, if nothing is in a table to design this, you can go to this method. What I mean by that is if you have a situation where the load is beyond the capacity is more than what's in the table. Anyway, so let's go back to the PowerPoint here. So this is basically the different cases. And subgrade, we talked about that, and case 4. Then you're gonna after you select the thickness, you want to check for shrinkage and temperature. You can use this equation, basically calculate it. It's nothing to it, and we done that in reinforced concrete design. And then you can do a different temperature method, and there's another equation right here. You can use this one here. I like this one. And then there's the equal strength method. That's a good method too. A lot of people uses this. You can do the crack estimate if you really get into the, if your slab is huge. Then fluctual stress, you got your actual stress has to be less than allowable stress. The bearing stress is kind of important because sometimes they have these posts on a small plate, the bearing plate, and you want to know, make sure it's going to make it. If not, you just have to make a bigger bearing plate. Punching shear is kind of important too. Make sure they're not going to have enough thickness, so you don't have an issue with the punching thickness. I do have a video on this, but in here you can just do a quick check using this equation right there. And this is about punching shear. We get back to this later. Oh, if you're hungry, pick one of these meals and let me know which one you like. Right now I just ate, so I'm not hungry, but I probably could go for, oh boy. This will look good though when I'm hungry. This good too. This is good with a cup of coffee. Bearing stress and dowel, and there's the equation for that. You can use this. And there are different slab types. You can look that up yourself. Let me keep going. Design objective. We get back to this in a minute. I'll give it to the problem right first. All right, let's do this example. So we want to design a slab on grade based on the following information. The concrete we're going to use is a 4,500 pound PSI. The lift truck capacity is 20 kip. And the vehicle weight itself is 22,000 pound. The wheel spacing is 42 inches. Tire pressure is 250 psi. And the geotech gave us the subgrade module of K is equal 200 PCI. Okay, let's get to work. Next, we're going to go ahead and calculate the wheel contact area. And the wheel contact area, normally the manufacturer will give you that. However, if the manufacturer doesn't have it, you can calculate it this way. We said the total load on a front axle was 42,000 pound. So on one tire, load on one tire is half of that, which is 21,000 pound. So I'm going to have here 21,000 pound divided by the 2 psi, 250 psi, and that gives me a 84 inch square. Next, we're going to go ahead and calculate the effective diameter of the contact area. To do this, let's go to the PowerPoint. I want to show you something here. We calculate the effective contact area. First, you're going to have the calculate the AC, which is the wheel contact area, and that's your load on top of one tire, and divide that by the tire pressure. In our case, our tire doesn't really have a pressure; it's a solid tire. Because it's a solid tire, the code says you can use 250 psi, so that's what we used. However, you may have the manufacturer tell you what is the contact area, and that's the best one to use. And if you don't have it, use this way. Once we find our AC, we're going to go ahead and calculate the A, effective load, and that's A is equal square root of AC divided by pi, and that's an apple pie. Okay, go ahead. So now that comes out to 517 inch, but then we have two tires, so really our A should be, in this case, because of two tires, 2 times 5.17, and that will give us a 10.34 inch. Okay, next we're going to go ahead and calculate the module of rupture, which normally for the slab design you really want to use a 9 time f square root of f prime c. Let me show you the PowerPoint for a second, and we're going to come back to this. Come on, there we go. So this is normally used, and there's a chart table on one of these. The ACI 360 has it. they have different value. But we learned in reinforced concrete design the module for rupture was 7.5 times lambda times square root of prime c. And why we use a 9 here is, well, this is like for cracking moment, but that's, in here we're gonna use 9, and that's good value to use. Let's go back to work here. So let me shut this off and we continue. And that's equal our was 4,500. So that will become we got 604 psi. So next we're going to go ahead and calculate the stress per 1,000 pound of axle load, and we're going to use a factor safety of 2, and our FB allowable basically is going to become MR divided by factor safety. In our case is going to be 604 divided by 2, and that will give us 302 psi. And so this is a number we're going to work with for now, 302 psi. I'm going to write this down again. FB allowable is equal 302 psi. Let's go to the PowerPoint. I want to talk about that for a second so you know what we're talking about. So the factors, we use this, and the factor safety is in the code. So if we go to chapter 5 and a load on here, it should give us the factor safety. That's the vehicle load. In this case we had our own, so we didn't have to use this. And there is a table here for factor safety. I know there is. Here we go, right here. And a factor safety used in design for various type of loading. And you can see 2 right here. 2 is a good number to use, so don't be afraid to use 2, because we design a slab on grade which they get really abused. So 2 is a good number. And that's what we did. So we got our attention become a 302 psi. Okay, so from here we're going to use the PCA method, the Portland Cement Association, and a lot of slab being designed this way 40 years ago and still standing. And in good shape too. So what we're going to do, we're going to take this 302 right here. We're going to take the 302, we're going to divide it by the wheel spacing, which was given in the problem. And the wheel spacing was 42 inch. And that's equal, that's 7.19 psi. This is a wheel spacing. So we take this, and let me go to the PowerPoint right here, and you can go ahead pick this chart up from PCA. You can use Google, or you can use ACI 360 has this also. So now we got that number 719. We're going to come up to here. We're going to go to 719. Just guess as the best you can. Then we go all the way across until we get to a area of the see these lines coming down, and these lines present 25, 50, 100, 200, and these the area we calculated ahead. It's the AC, or what we call it, the wheel contact area. So these are the wheel contact area, these lines, and we calculated was 84, and this line is a 200 and 100, so it's between just shy of 100, between 150. So we're going to click right here, and then we're going to go up all the way straight, and this right here, these lines represent the wheel spacing, and our wheel spacing was 42 inches. That's kind of hard to gauge because you see 40 right there, and then you see 60 right there. So we wouldn't just about guess at 42, close enough. Then we go all the way across, and then our module subgrade is 50, 100, 200. And if you above 200, there is a way you can extend this chart, but this chart only shows up to 200. So if you go all the way across, you're going to come in and our slab thickness is going to be about close to 11. See right there, that 11 is below 11. And the book calls it 10.9. So let's just say T is equal 10.9 or 11. Let me stop this right here. So this is how it's done. So our T is equal 10.9, let's say 11 inches for now. So that's how we calculate the thickness of the slab. But again, I want to go back and show you something right here at the PowerPoint we talked about. Right here, one thing I do not like about the code, they just don't use impact. A lot of time when you have a slab, you're going to have impact like this. Believe me or not, it's more common. You just don't hear about it. So the operator works and drops it and picks it up, and you want to talk to the owner, and maybe you can use the method that I have to prevent more damage. And what is that is what I recommend when you do your loading, you have the 20 capacity and your vehicle weight, add those two up and multiply them by 0.5 and make it add that to the total load, the impact. So that way you can count for the impact, and it makes it better. We will use this number later on when we go ahead and use the thickness method. We're going to use the Westgard equation. So this is how it's done using PCA. And let's go ahead and do the post load, see how we do that. Okay, so we're going to go ahead and do this example. It's on a post. We have a 5, 1, 2, 3, 4, 5 shelves, and it's 100 pound per square foot per shelf. The K is equal to 100 psi. The concrete is at 3000 psi. And when you look at the plan view of the shelf, it's going to be like 4 feet by 8 feet. And the base plate, that is the plate supported on, is about 20 inch square, which is a 4 by 5. Let me show you on a PowerPoint. Is we're looking at something like this, and a good picture of it would be right here, this one right there. So that's what we're doing. All right, let's get back to the writing. Okay, so what we did so far, we're going to calculate the module of rupture, which is basically right here. We did talk about that. Come on. And then it's going to be 9 times square root of 3,493 psi. The factor of safety you can pick out from the table 5.2, which we went over. Is this one? We can use 1.7. And then our load is going to be 100 pound per square foot times 4 feet by 8 feet times 5 shelving. That gives us a 16,000 pounds. 16,000 pounds right there. And we're going to calculate our allowable stress. FB allowable is equal, we had 493 divided by factor safety. That will give us 290 psi. And to go ahead and use the chart from a PC, use Portland Smooth chart. So we need to have 290 divided by 16 kips, and that will give us 18.1 psi. Well, let's go to the chart here. So this is an interesting chart. I'm used to using the equation, and charts are interesting. So here we calculated 18.1 psi per kips, and we're going to finally write this. And this is a chart from PCI book for K is equal 100. These lines are slanted. So we're going to slanted and come in, and the lines, and you can see you got down here you have 10, 20, 40, 80. That was the area of the plate. So it comes in, it goes into right here, we match with 20 at that slanted angle. Then we go straight across until we meet these 3 lines. And 3 line, remember I showed you we had the X and Y dimension on a rack, and that's the Y dimension, which was 8 feet, become 96 inches. Then from here, you're going to go meet this tree line, which is the X dimension of that was a rack in inches. Ours was 4 feet, and that's 48 inches. Meet right there. Then you really go across, and it comes out to 10.7 inches. That's pretty easy. And you probably be skeptical and say, no, this is just a chart that I don't see an equation. But believe it or not, a lot of slab been designed this way for many years, and they still stand in good shape. Okay, so this is it, and now we're gonna go to. While we're here, let's check out, see if we can pass bearing stress and punch and shear. Let me go back to the writing here. We can try this out. So bearing stress is our FP. Let me change color for good luck. FP is equal P divided by the contact area. Our P is a 16,000 pound divided by the contact area is a 4 times 5. That's a base plate, so that's equal 800 psi. And the allowable is given by the equation FP allowable for bearing 4.2 times MR divided by factor safety. So it's 4.2 times our MR was 493, and we used 1.7. That's 1218. So bearing is okay. Let's check punch and shear. And let me go to the PowerPoint. The punch and shear equation is given right there. Okay, so we're going to calculate the punch and shear. That was the equation I showed you. The shear due to the load comes out to 14 psi because our BO came out really big. I was surprised, 60 inches. And then the allowable, it's going to be 0.27 times basically the MR divided by 1.7, which comes out to 78. And 14 is less than 78, we are okay for a punch and shear. And another method we can try is chapter 7 of ACI, thickness design method. So I just took one of these equations. I don't know which one I took. I think equation case 2. I used the L, which is the radius of relative stiffness, and use this equation to find out, we'll see what the allowable stress is when we load considerable distance from the edge of the slab. And I have tried that different ways. So let me bring up the Excel, show you what I did. You can use this method too, but the other two methods were a lot easier. So if we're using the same tire, same example of one that we did, our F prime C is 4000. E, I basically calculated from the ACI code, which is equal to this one right here, 57,000 times square root of F prime C. And MR, I calculated based on 9 times square root of F prime C. Factor safety, I used 2. The allowable stress I used, I basically did MMR divided by 2, and I got this number. And then these are hand calculations right there. So then K was given us 200. P, I used 21,000 psi. It was 42,000 psi for axle load, and for one tire I just used 21,000. And then A for one tire comes out to 5.17, and the cracking moment FR based on ACI right here, and it's a 7.5 time lambda time F prime C, so that came out to 503 psi. So I come back in here, so okay, well, let's assume H. I did H. And then I put this equation right here, case 2, and I had to break it down to pieces to make it right. And at 11 inches, I get 643. That means it's not going to make it. It's going to crack anyway. if the cracking is 503. The next, what I used, if I use the axle load and increase this to 42,000 pound and hit enter, and then make this to a 10.3 for 2 tire, and that will give me 1200, way too much, so it didn't make it for I think this is made for like 1 tire. So let's go back to 21,000 and make this to 5.17 again, and that comes out to 643. So the 11 doesn't make it using this here, and let's make it to 12 and see what happened. 12, enter, I will bring it down to 576. That's not bad. And if you want to make it 18-inch, enter, that will bring it up to 349. So this, you can use these equations. They're kind of pretty cool to work with. There are different ways you can calculate the thickness for the slab on grade. The easiest, the best way was using PCA. But if you ever want to do this at a professional level, make sure you have a ACI 360-10, and there's a lot of good examples and different method there. Check for all the criteria that I had on the PowerPoint. Let me bring that up. I want to show you. Just make sure you check these. Minimum required slab thickness, which we did there. Required shrinkage temperature, that's easy. Just plug in an equation. Estimated crack, slab flexural stress, and the bearings. We did the bearings test in the punching shear, which was kind of good. And these are just a simple equation you plug in, and I showed you on the PowerPoint how it's done. I hope this video was helpful. If it was, give it a thumbs up, and I'd like to hear your comment. You have a good day.